Hello, everyone, and welcome to Why Distributed Edge Data is the Future of AI, brought to you by the SNIA Cloud Storage Technologies Initiative. I'm Erin Farr, your moderator for today's discussion. I work for IBM and I serve as Vice Chair of SNIA Cloud Storage Technologies Initiative. Today, we have two excellent speakers. We have Rita Wuhabi, Senior AI Principal Engineer, Office of the CTO in the Network and Edge Group at Intel. Hello, Rita, how are you?
Hi, Erin. Thanks for having me. I'm good. How about you?
I'm good, thank you. And we have Heiko Ludwig, Senior Manager of AI Platforms from IBM Research. How are you today, Heiko?
I'm excellent. Great.
Thanks. So first, a little bit about SNIA. SNIA is an industry organization that develops global standards and delivers education on all technologies related to data. So SNIA is comprised of 200 industry-leading organizations, 2,500 active contributing members, and 50,000 participating IT end users and technologists worldwide. And the SNIA Cloud Storage Technologies Initiative, or CSTI, is an active group within SNIA that helps advance standards related to the cloud. We provide vendor-neutral education like this webinar on all technologies related to cloud. So just some logistics for today. You can ask questions during the presentation by selecting the Ask Question option and entering your question. We will probably hold questions until the end, though, so just be patient, please. And the slides are available at the Attachment tab at the bottom of your console. And finally, last thing before we get started, let's take a quick look at the SNIA legal notice. This provides SNIA's copyright notice regarding use of the material. So SNIA is not providing any legal advice, and there are no warranties expressed or implied. So if you want to reference this material, please do so at your own risk. And so again, welcome everybody to today's session on distributed edge data and its impact on the future of AI. Today, we will discuss the use cases and lifecycle of edge AI. We'll talk about what is new and different about edge data, and then we'll cover some federated learning at the edge and how to deal with not having shared storage, and finally go into some privacy concerns for edge AI. And then we'll open it up for Q&A. And with that, I will turn it over to Rita.
Great. Thanks, Erin. It's great to be here today to share one of my favorite topics, which is edge AI. And I'm very excited to team up with Erin and Heiko on this topic. And what is edge AI? Why does it matter? Why do we do AI at the edge? I hear those questions all the time. And a lot of times when working with customers or specific OEMs and ODMs, and they are struggling of when to place AI at the edge, when to place it in the cloud. Why are we talking about edge AI? There are often three areas that people talk about. That's the answer to the why. The first one is latency. If you are operating in an operating room in a hospital, if you are trying to control a robotic arm in a factory, sending all of your raw data, all of your sense data, whether they are video cameras, they are time series, they are audio, whatever the modality is, sending all of this data to the cloud, and then receive back an answer from the cloud where compute often resides is just too long, right? It might be someone's life at stake. It might be building a specific car or a specific product that is at stake, and waiting for a response to come back from the cloud is just not feasible. So that's the first reason that we hear over and over again, which is latency. The second one, which is a very important reason, and Heiko is going to target this topic very specifically, is around privacy. There are a lot of rules and regulations in some geographical locations, especially Europe, around what data can reside where. But there is also intellectual property. There are a lot of other concerns around privacy where perhaps you don't want the data to leave a specific geographical location. You want the data to stay close to where it was generated and continue to be owned and managed and observed by the entity that generated it. So that's another reason for not sending the data to the cloud. And the last one is bandwidth. A lot of times we are generating so much data. It's actually really funny. For years now, I have been hearing people talk about data being the next oil. I wish data was the next oil, because honestly, we keep generating so much data as a community, as humanity in general. And I don't know if it is the next oil. I would rather think of data as the next water, right? It is something that we're going to generate a lot of. It is going to be our right and responsibility to use and use appropriately, but it also is going to require some effort in managing it. And it's not going to make us money by just existing there like oil. It is actually going to be some work, some introspection, some analysis that goes into it, because you know you can't just generate it and dump it, right? The analogy here of water is actually quite fascinating, because if you dump water when you generate it, you either lose it, or if it is internally and it's not in a place where water can be processed appropriately, it might create mold and other problem. And honestly, data is the same, and sending it all to the cloud is have reached in many use cases actually the not feasible status. It's not feasible, it's not physically possible to send all the data that we're generating right now at the edge. So if we think about it, us as a computer science community, a couple of decades ago, we started switching all the compute to be consolidated in the cloud, and we sent the data to the compute. Because at that point in time, I would argue that we thought as compute as more important than data. And now we're seeing a shift. We're seeing a shift where data and its importance is becoming more important or equally important to the compute. So I would argue that edge AI and edge computing in general is about switching that balance to the other side, is about moving compute to where the data is getting generated. And that's an interesting concept. And today I will talk a little bit about what does that mean for AI. As an AI community, we have made few assumptions when we created AI applications and AI models, and did all kinds of awesome innovation around AI. We made some assumptions that edge AI might be breaking. What other challenges are we looking at? Again, working with customers, I often see additional challenges that come in addition to the top three to the why. The first one, a few years ago, when I started on this journey of edge AI, it used to be where training happens in the cloud, inference happens at the edge. Everybody was really happy. And we're seeing that continuum break. We're seeing inference happen in the cloud, obviously, but we're seeing also retraining, fine tuning right now with LLMs starting to happen at the edge, starting to happen on prem of enterprises, starting to happen in people's pockets on cell phone, starting to happen in all kinds of situations. And that's an interesting mindset. We're seeing that loop of inference to training happen much, much quicker as well, and in all kinds of deployment scenarios. Add to that that often the edge application, when you are doing AI at the edge, you often not doing it for kicks and giggles, right? There is a use case, there is a reason behind driving that application, and that application is more than just AI, is more than just inference. You have a full pipeline. Your pipeline includes managing your sensors, how you're ingesting all this data, what you're doing with the data, running the inference, perhaps publishing your result, storing some of the data, deciding what to store, and if you are customer, if you are user facing in your application, you might want to visualize some of your results. So this whole data pipeline is more than just inference. And again, there has been a lot of focus around inference. But again, working with customers, I find it very important to talk about the full pipeline and how you're going to manage it at the edge. And last but not least, again, like I said, you're often not doing it for fun. There is a business logic. What do you do? What do you do as an output of this edge AI? It depends on the use case. If you are looking for defects using computer vision in manufacturing and you found a defect on a product, do you stop the line? Do you alert an operator? Do you take an action with a robotic arm to remove that defective product? Do you change your process so that the next product is not defective? There are a lot of decisions and a lot of potential paths that you might take. So all of those are really important. How do you close that loop? What is your business logic for your AI use case? And thinking about all of those holistically is often essential for the success of edge AI. let's talk about how does it happen? How does the magic happen? From the moment someone says, I have a problem and I think AI can help me solve it, until you have a full deployment. And these are typically the phases of AI at the edge. They differ a little bit from the phases of AI in the cloud. And what's very interesting is that we have what we call few persona handoffs. We have few experts that need to come together to create those applications. Now, as I'm talking through these phases and walking you through them, I will share with you that as a data scientist, my mission is to make these phases as seamless as possible. I really believe us as a community, this is not a sales pitch, but us as a community, we need to make AI more consumable. And in order to make it more consumable, we have to think about the entire stack of software and hardware and use cases and personas, and how do we bring them all together. That's really important, because if AI is going to proliferate, people should stop thinking that they are using AI. I often joke when working with customers and I, go to meet with them, and they are sometimes in awe, sometimes a little critical as well. In addition to being in awe with AI, and they start discussing with me that we want to introduce AI, we want to use AI, and so on and so forth. And honestly, I often start by telling them that if the AI community does a good job, you will start using AI without thinking it's AI. And the analogy that I give them is, I say, hey, did you wake up this morning and say, oh, I am so excited. Today I'm going to use advanced analytics? No, you didn't. No one does that anymore, right? We all use all kinds of advanced statistical methods without thinking about it. They're very complex. And no one really thinks about them as complex. They exist as black boxes. They are part of your toolbox and you use them. And we have to get AI to that stage. If we don't, if it continues to be complex, and 5 years from now, I still present AI at the edge with a slide, that has these many phases, then honestly, I would consider myself to have failed at my mission, right? My mission is to make this as seamless as possible. However, let me walk you through it today in the handoff and personas in making edge AI successful. Typically, it starts by someone presenting a problem, saying, I have this problem, right? I produce cars, and some of my cars might have defects, and I want to catch them as soon as possible. Or maybe I want to do root cause analysis. I want to figure out why they are coming off the line defective in order to reduce or eliminate these defects. Or someone else could say, I want to assist in an operation, or I want to assist a user doing some form of a labor in a warehouse. So whatever the application is, right? You define that use case and you define the KPIs. And believe me, working with many of those use cases with our customers, I have found that that's probably one of the hardest steps in here, is defining that use case and how you're going to measure success. A lot of times I would work with customers and they're like, well, I want it to be better than what I have. Okay, well, let's measure what you have. Do you have some form of measuring it? So don't underestimate choosing a use case that you can actually measure success. Because again, most businesses are not going to introduce AI just for fun. This is a business decision that needs to happen. After that decision happens, after that use case is defined and the KPIs are well articulated, then you need to collect some data, right? Again, going back to, is it oil or is it water? Irrespective, you're gonna need some data, and you still need to label some of the data, if not all. And here is where there are a lot of AI techniques. Do you label all the data? This is more the traditional supervised AI learning, or do you do partial labeling and you use either semi-supervised or unsupervised learning? There's a lot of advancement, and this is one of the area that I am very excited about. Academia and the industry are working hard on making AI more consumable by simplifying, even from the beginning, the data collection and labeling. After you've collected this data and perhaps labeled some of it, you will transfer it somewhere. And this is one of the first handoff that happens. Typically, again, let's take some of the examples. Let's say I am working with manufacturing. This is where I would start working with an OT operator. It could be a control engineer. I've worked in the past with a welding expert, with a car manufacturer, and they collect all the data. Now I have the data, they're going to transfer it to a data scientist. This data could be images, could be text, could be numerical, whatever modality it is. The data gets transferred and aggregated. And it could be that you've collected data from multiple places. Maybe you have some ground truth that is part of your quality control that is hosted somewhere in the cloud versus some data that gets generated at the edge. So once you transfer the data, you did a handoff from a subject matter expert, from someone who, again, is a control engineer or a health professional, whatever the application it is, to a data scientist. And the data scientist at that point in time will decide based on what technique he or she is going to use whether they need to further do additional labeling, right? It could be that, again, I've collected data. They are defective images of defective products from a manufacturing line. And the control engineer who collected, or the quality expert who collected that data, labeled few examples of defects. And that's where the data scientists will decide, are they going to use some form of image clustering and they don't need to label more data, or do they need to label the rest of the data because they're using more traditional supervised learning techniques? And then they get going on the AI algo. Depending on the audience, they might imagine where this data scientist at that point in time is going to do something between art and magic and science. In the AI algo training, they're going to figure out basically based on the data set and the use case and their experience, how are they going to train this model on state of the art. They could have at their disposal an AutoML, which basically helps them in making that decision and identifying what type of AI is the most appropriate for this use case, and then go about using those techniques. At the end of it, they generate an AI model. The AI model at this point in time, they need to make it a full application, because we talked about the inference being more than that. So they need to package it. Maybe they have few trade-offs in here. Do they need a very accurate model or a very fast model? Often during training, you have those trade-offs to play with. So you make those decisions, you generate one or more models, you get them ready to be deployed at the edge, because again, we talked about it's more than just the inference, it's the full pipeline. How you're going to ingest the data, a real operation, online data, how you're going to feed it into your AI pipeline, and what you're going to generate, and then you deploy it somewhere at the edge. So it's typically not the data scientist who deploys. So in here, we experience another persona handoff. This is where a data scientist would hand it off either to an IT department, maybe in a big retailer, or to an SI that contracts with a hospital or a factory or what have you. And the SI will do this packaging. They might even get a device, a computer, a box, and deploy that application. And then they will have to go to the actual enterprise or where it's going to get deployed. Maybe it's a pipeline, it's an oil pipeline in the middle of nowhere where they need to deploy it. They have to figure out power sources and cabling and routing, and do they have access, to the right policies in order to get the data, and so on and so forth. So it's not actually trivial at all. There is a lot of work that goes into it, in addition to it being a persona handoff. Then you test the model. So often when you are in critical applications, especially, you don't just show up and start running it. You often test it in a POC environment. Maybe you test it in one cell on a factory floor, and then you use the output just to look at it, to analyze the output over a period of a week or two. And then, does it pass your KPI? If it doesn't, you might go back and collect more data, or to any parts of these phases in your life cycle. If it passes, then you scale it and you maintain the solution over time. It's a complex process. Are there payoffs? Absolutely. Is it difficult? Do things fail? I think probably the audience have heard of AI at the edge, not going beyond POC at a very alarming and high rate. And in here, I want to highlight that not only is every phase really complex, but we have few critical handoffs. And sometimes we have seen those handoffs break. This handoff from a data scientist to an SI, maybe the SI doesn't have the experience of actually taking it to scale. Or maybe we didn't collect enough data, going to the subject matter expert, and at that point subject matter expert says, go away, I've given you all I have, I don't have time for you anymore, whatever it is. So that's really a call for us as a community, that there are still a lot of interesting and open challenges for us to solve and make those phases go much quicker, in the background, automated, and so on. What are some edge use cases? There are a few big bins of edge use cases that I have seen, but also a few big bins that if you look at any of the reports that get generated by the big players, whether it's Gartner or McKinsey or any of the market analysis, you'll see them bucket use cases into families of use cases. And here I want to, walk you through some of the examples. I personally have extensive experience working with manufacturing and introducing AI at the edge. More recently, I started working with other domains. So that's why you'll see me talk about use cases coming from manufacturing, where AI is really making factories more and more efficient, more green, more productive, more friendly to humans, and so on and so forth. I know Heiko will describe other domains as well. So the first set of use cases often fall about how can I better predict and reduce downtime? So you might have heard about things like predictive maintenance. Can I predict ahead of time that a device is going to go down? Can I predict ahead of time that something out of the ordinary is going to happen to my process? And if I can predict it, how can I mitigate it? Can I go change the battery on my car before it actually leaves me stranded somewhere, and so on? The second one is how can I meet the rising requirement on product quality, right? We are, as consumers, demanding more and more product quality out of our suppliers. Can you use AI to improve on product quality? I've worked on a use case with Audi manufacturing in their cars. I can talk about it publicly because they have went publicly on record about it, where we looked at introducing AI to improve the welding process, to find defects in welding and potentially be able to eliminate those defects using AI. It was a great use case of how AI can be introduced to create a better environment, to create a better product and make the world really a better place as well in that process. How can I optimize operation for higher throughput? So instead of zooming in on a particular use case, this is the big picture, right? We see a lot of examples in warehousing, how to optimize some of the shipment, how to optimize loading things into a truck so that it's more energy efficient. How can I organize the process of different workers in a particular space so that they are less in each other's way, and so on. And then the last one is how can I leverage AI for better business outcomes? And we've seen this at the macro level, right? How can I not just create a better product, but also do root cause analysis, as well as business intelligence kind of applications. Why did something happen in here? Can I look at the micro as well as the macro level? Is it because I changed suppliers? Now I'm seeing more defects. How can I optimize this? How can I provide to them this feedback in a secure fashion and trustworthy fashion? Okay, great. We've talked about AI and use cases, but we're here as well to talk about data, because at the end of the day, AI is a set of tools, and without the actual data, AI is a tool waiting to be used. So, what is new about data? What are some of the challenges of edge data versus cloud data? For the longest time, as an AI community, whenever we thought about designing AI and coming up with the best, we thought about all data aggregated in one place. And there are challenges in doing so, obviously. However, some of those challenges have been resolved over time. So if you look on the right hand side, the cloud data, for the large majority, is aggregated data. It follows one policy. You can, a lot of times when you're in the cloud, of course, it might cost you more, but creating elastic and abstracted compute is very feasible and very easy. And often it's highly available, right? It's static, it stays there. It's, if a big cloud service provider experiences downtime, that's a problem. Everyone would hear about it. So they're gonna maintain a very consistent uptime. Well, in contrast, looking at the left-hand side for edge data, you'll see that edge data is highly distributed. I might have 1,000 camera on a factory floor looking at the conveyor belt and the products moving on the conveyor belt and tracking these different products and the actions that are happening to them. All of this data is distributed across those cameras and nodes that they are attached to them. It might crosses boundaries in manufacturing, in hospitals, in retail stores. Often people who are operating that location are different than the IT department that manages their machines and their data and what have you. And this is where AI and data causes friction. And we sometimes see some of our customers, after they have started deploying AI, you see them reorging structurally in order to be ready for more data and more AI. And that's actually really fascinating because edge AI, we're seeing it change how organizations operate. We have a lot of heterogeneous compute. You can't abstract it very easily. You might have a lot of suppliers. Again, in manufacturing, there are multiple robotics companies and suppliers, and they tend to use different data formats and protocols. And last but not least, it's very dynamic. You might have cells that come down, you might lose connectivity. No matter how good your infrastructure is, it fluctuates more than a data center. So, what do we need? We really need to get to a place where data can be abstracted, where my customer no longer cares about where the data is coming from. Remember how I said they have to wake up in the morning and not think that they're going to use AI today? So, in order to get there, we need to create elastic compute. We need to abstract where the data is available and how to query it. And we need to create an easy way to experiment and iterate very quickly without having to set up every time a network and devices. Because remember, in my thesis, I said you need to test your new ideas. If we inherently create a way where people can test ideas and innovate at the edge, it's going to get them more excited to use those tools. There are a lot of advances happening in AI. I am sure the audience in here have thought about or have read about or have considered how to use LLMs. And large language models are very important. And in my opinion, have kind of turned the table of saying, what if AI was so easy you could just chit chat with it? And I'm not saying LLMs are going to solve all the use cases, but that concept of making AI more consumable, more accessible is definitely a very interesting one. That we need to break that barrier where AI feels intimidating. And we need to rethink the persona of AI because honestly, data scientists are not cheap and are not easy to come by. We need to make AI, again, like we use many tools today, like we use stochastic and queuing theory every day in many applications, and we don't even think about them. Many of the people who are using it can't even name that they are using these techniques. At the end of the day, AI and the data that runs it need to become a tool that people can swap it in and out without really having to think about, this big shebang that they need to do. With that, I hand it off to Heiko to walk us through additional interesting use cases.
Thank you, Rita, and thanks for the great start. So I want to talk a bit about the specific use case in which we actually use the edge as or include that in the learning process, right? A lot of current applications in AI at the edge are more on the inference side, how you use the models to get something done. But as Rita was pointing out earlier, um, not only is it relevant for inference, but also for learning, with the spirit of bringing the compute to the edge as opposed to the data, as opposed to collecting the data in a central repository. So in this case, I want to talk a bit about federated learning, which is a learning method that is decentralized and does not require us to share data with a central entity. Go ahead. What is it? What is federated learning? It's pretty simple at the outset. It is at its outset. Imagine multiple parties, in our case, edge devices, train a machine learning model. So one machine learning model, collaboratively without sharing their training data. So everybody keeps their training data, nobody shares training data, and collaboratively we train one model. And that's kind of the idea. So how can we pool data? And there are a lot of use cases for that. In particular, in primitive or high volume data cases, in the way that Rita already has introduced it earlier in this presentation. One case we came across is neonatal care. We work with a company, Innocence is the name of that. We can use that. Um, they're interested in sepsis in early born children when they are in these little beds in hospitals. Apparently, sepsis is the most frequent cause of death in infants. And so they would really like to study what contributes to sepsis and predict it earlier than maybe a nurse or another clinician could do in a hospital. And these babies typically lie in these beds, and they have a lot of sensors in these beds, right? About 200 actually. And in this case, they monitor all kind of vital signs of the baby. And in this case, given the few hundred sensors and time series, it was important to have a good database, which you might not necessarily find in one particular hospital. It was a Belgian-based company. And in this case, the idea was to team up between multiple hospitals that all have similar beds for neonatal care and train a joint sepsis prediction model on the basis of more data. It actually worked quite well. In this case, we had trained a gradient boosted tree, so a tree-based model, which in clinical environments often helpful because it's more explainable than maybe deep neural networks, but it could have been anything. So it was kind of a very interesting use case where privacy obviously plays a big role in this scenario because obviously medical data, in particular sensor data, is quite protected in all legislations, but also particularly in Europe. In another use case, we worked on environmental modeling. This was very different in the way there was a deep neural networks about visual inspection, identifying flare tips and clouds and so forth. In this case, there's a lot of issue of data sharing, what's going on in oil fields, either between various investors of the oil fields or equipment manufacturers and oil field operators. So in this case, it was a deep neural network, also very edge-oriented. And in this particular case, also there was access to energy and to bandwidth and to compute, such that these environmental training models could be improved over time. So it was kind of a regular retraining cycle where they would be improved, and also then when a new oil field came online or a new stack came online, they would have a training cycle to adjust the overall global model to the new conditions that are found in this particular environment. And this is kind of an optimistic picture. Typically, these are cameras overseeing a whole kind of sea of production equipment with many different flares, and so that's kind of a really tricky identification in this case. So we find a lot in this environment as well. Other ones, I think, Rita, you already alluded to in manufacturing, there's quite a bit, and because we often find a situation that you have an equipment manufacturer, let's say a welding robot, or a mobile company, would like to improve their, let's say, the visual capabilities, the visual identification of welding points, for example. But the actual data is owned by the car company that manufactures on this line, but it's really the robot vendor who would like to improve this scenario. So there's a lot of opportunities to collaborate and have use cases for a federated learning environment in which you train collectively a model, but you would really like to keep the data where it is and not share it with anybody. So how does it work in principle? So different variants, but its most basic form, it has two kind of participants. The one is an aggregator whose role it is to kind of coordinate the overall process and to aggregate the model. This is sometimes referred to as server or any other way. And then a set of parties, and the parties will be our edge devices in our case, or groups of edge devices that train jointly, and they would all collaborate to train this model. Each party has its own data. The data never leaves um, the edge device or its domain, who has it. How many parties can you have? That depends a lot, from a few in some cases to millions and millions if you think about a cell phone use case, right? And the whole process would roughly go like this. You set up the whole environment and list the parties, connect them to the aggregator, and the aggregator would distribute the model structure to be trained, kind of the seed, to each individual party. Then you start and basically say, oh, let's do the first round, and the aggregator queries each party about a model update. Then each party will perform local training for a few epochs. So if we talk about the deep neural network, so you train, say, 10 epochs on your local training data, and then what you do is you pack up a response. For example, extract the weight vector of your deep neural network, and let's say some other parameters, for example, the number of samples that you used in your training process, and then you send them back to the aggregator, right? And the aggregator collects them from all the participating edge devices, and they, for example, the children's beds that we saw, and then the aggregator puts the model together. It fuses the model, or it merges the model, and that there's a ton of different algorithms to it. But in its simplest case, people typically do a weighted average of the weight vectors. So you have the weight vector of a deep neural network from each party. You know how many, let's say, samples each party used, and then you use it as a weight and compute the weighted average, right? And then once you did that, you did this averaging, you go into the next round. Basically, you send the next query back, including the merged model. That's the new seed for each party. Party performs local training based on this new merged model with its local training data and so forth. And you do this over a number of times, and each kind of sequence of local training and merging is called a round, as opposed to the epochs that take place at each party. Why do you do that? Why don't you just, everybody trains their model and then you merge it after? The approach is to do that as well. The problem is often then if that the data distributions between the various parties is different, right? So they're not quite the same. And in this case, there's a tendency of parties to really optimize in a local minimum, and then if you merge them later and, let's say, take the weighted average at the end when everybody has trained, is that the resulting model is not very good in general, or doesn't generalize well to all the parties. Whereas if you do that all the time, and let's say do 10 local epochs and then a communication round, then you typically achieve a decent result in bringing this all together. It all depends a little bit how different the parties are in their data distribution, and that's kind of an important aspect as well. If you have different independent parties, data is drawn from different distributions, so there's something to account for. There are a number of methods related to that, how you deal with this, but that's kind of the basic thought. Now, if you have very few parties, few edge devices, children's beds, and so forth, you would only involve them. You would involve them every single round, right? But sometimes, if you have a very large number, let's say cell phones, and you train for a cell phone application, you wouldn't enlist 300 million iPhones or something. That's too complicated. That's too much. If you have 300 million app users, for example, what you would do is you subsample in each round. You would randomly pick, let's say, 10,000, and then maybe wait for the first 1,000 responses, and then use those as the basis for the fusion algorithm to merge the models. If you have a smaller number, let's say this hospital beds that we just saw for neonatal care, also sometimes you like to involve all of them, but sometimes there's just not all beds are occupied, right? So they might not be all available. So in this case, that's fine as well. You have communication cutoff or quorum and so forth when you think it's a good idea to do that. Also, obviously, there might be different children in the beds over time, so the data distribution again might change over time for each individual party. But that's a good thing, right? The advantage is you can benefit from the different data distributions of all the different edge devices, forming a model so that in the end, the resulting joint model represents the experience of everybody without really needing to share the data centrally. So that's good, and there are many good use cases for doing that. That's kind of the basic form. There are lots of variants, in particular fusion algorithms that take into consideration difference in data distribution for all kinds of things. A similar class of fusion algorithms also works for all kind of models with a static model structure. Say simple linear models like linear regression, right? That we can actually train quite well in a federated learning way. A little different are tree-based algorithms, where they don't have a fixed model structure. Typically, what you do is you grow a decision tree in the aggregator, and then you would see how the tree performs on the party's data, and work with that. So there are different variants of that. So oftentimes, so you repeat this a number of times for depending a bit on the size of the model. And but you see something like 10 to 100 to maybe a few thousand rounds would probably get you there. And figuring out how many epochs locally and how many rounds globally you need is one of the data scientist's task in doing that. All right, so that's kind of the basics. As we said, no data is ever shared. Everything remains where it's stored, and that kind of is really a good starting point for data privacy. But on the other hand, a lot of machine learning tasks traditionally depend on looking at all the data. For example, hyperparameter tuning, right? So finding the right hyperparameters, the learning rate, how many epochs, and so forth. Sampling strategies. That's kind of an important part, and hyperparameter tuning is typically performed here. Often it's automated. There's a lot of automated hyperparameter tuning out there. Many tool vendors offer that. Federated learning makes this a bit harder because you can't access all the data, but it also introduces new hyperparameters, like how many rounds and epochs you would choose, right? And maybe which parameters you would exchange. So it's a bit more tricky. There are a couple of approaches that really deal with that, and why I'm pointing out a particular one here that we had worked on is really show you the principle of how you deal with that. If you don't have all data in one place, you basically replace it with some local action and a protocol. So the idea is here in this case, you before you start training in a federated learning way, you do a federated hyperparameter optimization process. You basically send your model and to the parties train and vary kind of the set of hyperparameters to generate a set of hyperparameter and loss pairs. So they would evaluate the model performance and how it's progressing. And you do this for each party, and that's what you send back to the aggregator. And then in a way, similarly, a bit more complex than kind of performing this fusion algorithm, you would merge in principle here, in this case, create a unified loss surface of all these different combinations of hyperparameters and loss and kind of bring them together. And then that typically yields a pretty good set of hyperparameters that work for all parties in a way to create a unified model. So that's pretty good. And so this is one example of how you address a problem that you typically solve in federated learning by looking all the data in centralized learning by looking at all the data in a central place and replace it with a protocol and some merging activity. Another point where you do that maybe is related to fairness and bias mitigation. Obviously, this is very important. Fairness and bias are problems that need to be addressed in many ways. And if you carry bias in your training data, then probably you carry it into the model as well, right? There are a number of bias identification and mitigation efforts. And so in this case, but again, traditionally they would depend on looking at all the data, analyzing statistical bias over the whole training set, and then maybe do subsampling and so forth, different strategies to mitigate the bias in the final model, right? Or generate new data. There's a lot of different strategies. And the solution here is basically of a similar nature that we found in hyperparameter optimization. What you would do is then you translate these approaches into a federated approach where you have, say, people would analyze their statistical bias in their local data set, the different parties of different neonatal care beds, and then you would introduce that and send your parameters back to some abstract representation of how your data looks like. This can be taken into consideration by the aggregating. You would merge that, for example, by local reweighing, or there's a process called prejudice removal, and you create a federated representation of that. And with that, you can perform this bias mitigation, say, either as a pre-processing or in-processing step in that context as well, in a federated way, by having some aggregation and some protocol. That's mainly as an example. There are many other ways of other problems that you solve with a similar approach, just picture, fairness, and bias. Wanted to talk a little bit about the privacy in federated learning, and I really like this graphics here on the right side that we had taken here from you see here the GitHub repo where it really comes from. It's not from us, but it's a really good illustration. What it shows how training data can be recovered from trained models, and that's a property that's not particular to federated learning at all. That's relates to a lot of classes of deep learning models that are kind of representational and kind of memorize a little bit the content of the training data to some extent. And there's a bit scramble here in our graphics here, but the idea would be that you have different points at which and different points at which you can basically attack or create inference from on a model in a federated learning case. In a centralized learning case, you usually have you get the model at the end, and you can run a membership inference attack and maybe reconstruct the face of these gentlemen that we see right here, right? And then who is that person? How does this person look like? And then you might get the picture, which is kind of tricky from a privacy perspective. In a federated learning case, you have more attack surfaces that might be of concern. Say if you send weight vectors to the aggregator, right, then maybe you can also, from the resulting merged model, you can maybe infer, if you don't have very many parties, for example, what another party's contribution might have been, and infer some training data from it. So there's a little bit of additional vulnerability that needs to be addressed. And luckily, we have a whole plethora of privacy techniques, and I'm going to go through all of them. I just wanted to throw some at you. And one that's typically used is differentially private noise. You can add differentially private noise to your particular training data, or clip the model if you like. So there's a whole different set of strategies how to apply that, and different distributions from which to draw the noise. And what that typically does is it really is quite effective at preventing membership inference attacks. However, as you might imagine, adding noise to data doesn't exactly help with the performance of the resulting model. So you have to be quite careful how much noise you distribute. And also, what you can do is you can kind of make the aggregator blind, and there are different techniques how to do that. You can use a fully homomorphic encryption. Maybe there are approaches based on functional encryption with a third-party authority. There are functional encryption using a decentralized multi-input functional encryption. It's MIFI here. And there other partial homomorphic encryption approaches like palier and threshold palier and so forth, secret sharing, a whole lot of them, or hardware-based solution like trusted execution environments. And while they are typically computationally heavy, the aggregator typically would not run in an edge device. The aggregator you typically place in a cloud if you can, and thereby it can avail itself of accelerators. I think a number of companies, including Intel, have hardware accelerators for something like homomorphic encryption or have trusted execution environments. So that's something that's quite good to integrate. Want to give some idea. Sorry, this is a bit garbled here. The idea is then if you add a lot of noise with individual, say, children's beds, then your model performance goes down. But if you disguise where actually the updates come from by performing the aggregator or doing the aggregation function in a multi-party computation way, for example, with a palier scheme or threshold palier scheme, then you can reduce the noise you actually need to do and in the end have a relatively reasonable model that works. And this is kind of an illustration how multi-party computation works. Basically, imagine on the left side our parties, our kids' beds, and we collect data, and once we have train our model, we encrypt the model update with a multi-party computation key and send it over to the aggregator. That's the box on the right side, and the lady there, and so it's kind of enclosed in this box we can't really see, and then the aggregator would then do the merger on encrypted data, really, so not visible to the aggregator or not in plain text, and send the encrypted model update back, and then each party can then decrypt the model and has the model without the aggregator ever seeing an unencrypted model update. So that's really quite convenient. It's pretty good, and it works relatively effectively. Running with short time, so this usually works quite well. We tried that out, and this is one way of illustration of combining different cryptographic models methods to really achieve the goals of combining privacy with effectiveness. And I think that's kind of brings me to the end, and I want to pass it back to Rita for the summary.
Sorry, my unmute was not quickly available. Thanks, Heiko. So going back in summary, really AI is changing, and edge is one of the pushing factors in changing how AI is going to look like into the future. I think many of us are very excited about those changes because it creates new opportunities for innovation and new ways where AI can be applied for a plethora of use cases. So just like AI is changing our environment, the edge is changing AI. I hope here you heard us about some of the challenges we are facing and working on from all different angles when it comes to data. Data is complex, it's noisy, and it's distributed at the edge. But at the same time, as a technologist, those things excite me, and as you heard, excites Heiko quite a bit. We are working on use cases that are very important to people and to creating really a better world. And solving the data challenges is really essential. I feel very strongly that AI is one of those areas where if we do it and do it right, it will create a better world for many, many people around us. Join us today in innovating around AI and edge. And this is really a time where we're going to see an explosion in this domain. So thank you, and would love to take some questions from everybody.
Yes, and just a reminder, we'll open it up for Q&A, and you can ask questions by selecting the Ask Question option and entering your question. And here we can start with one question. With the rise of large language models, what role would edge AI play?
I'm happy to take that question, Erin, and Heiko, feel free to chime in and add. So LLMs are very exciting, and many things are happening for LLMs. Most of the time, they are very large models that we think of as operating in the cloud. However, we're seeing LLMs as one tool in the toolbox. And if I were to see it as one tool in the toolbox, one of the powers of large language models is their ability to predict events. And today, one of the ways they operate, or at least some of them, is by predicting how a human would answer a particular question. So, a domain that is rising in popularity right now is, can we take that prediction power and use it in other domains? Can I show the LLM data that's happening at the edge? Can I show power consumption perhaps, and have it predict what is going to be the power consumption tomorrow of a particular device, of a particular institution? How would that help me create a better and more efficient routing of maybe a grid solution? Or maybe internally, can I reconsolidate workloads that are running on a factory floor or in a retail store to minimize my my power footprint? So this power of predicting that LLMs possess is very, very interesting, and we are actively looking in that family of use cases. That's not the only one. This is only one of the examples where LLMs will be used at the edge.
I think it's also interesting, if I may add to that, an interesting use case of combining a centralized learning approach with for creating foundation models with maybe an edge-driven approach to create or fine-tune the model, right? So if you look at LLMs, typically as we have them, they're trained on very large amounts of data, and they're also very big, very large parameter vector. So anything federated on that is quite expensive. However, if we had if we assume that the foundation model is trained on public data, and you would like to fine tune it to, let's say, the needs of a particular community, you could at least try to run a fine tuning step that creates a particular application specific model in a federated learning mode while preserving privacy.
All right, and I think maybe we have time quickly for one more question from an attendee. Do you have any measurements about energy usage for edge AI? Wondering if there's an ecological argument for edge AI in addition to the others mentioned.
Yeah, absolutely. Actually, it's very much use case dependent. It is hard to come up with, one universal number. So it is one way I can share with you that it is one way that our customers are looking at some sustainability. Is not just, what is edge AI? How much does it cost in terms of power and its green or power consumption in general, and whether it's green or not at the edge versus in the cloud, but also the use of AI for creating more sustainable systems for the edge. So looking at both ends of the story in terms of sustainability.
And then, Heiko, I'm not sure if you had anything to add to that.
Yeah, I think it's well said. Obviously, in one of the advantages of edge deployment is often that it forces us to have a smaller model size, let's say quantize it or compress it or distill it or whatever the technique is you'd like to have, and then at least for at inference time have use a more efficient model. So in that respect, kind of driven by need to do that, we can actually probably save some energy and create a smaller footprint.
Thank you. And so that's probably the last question, given we're almost to the top of the hour. I want to remind everybody you can go rate this presentation. That's important to us as it gives us a solid indication of whether we are delivering the right quality of content. And so I want to thank you very much, Rita and Heiko, and thank you to our audience for joining us today.
Thank you.
Thanks, everyone. And thanks, Erin, for hosting.
Thank you.